All right, greetings. In this screencast, I want to work out some simplified expressions for computing partial molar properties in binary mixtures. And so first I want to motivate, right, exactly what we're trying to accomplish here. And so for the case of binary systems, if I'm trying to develop analytic equations for my molar properties, right, of my system, typically I'm developing analytic equations that are a function of composition, right? So here, composition and Wolfram. And so if I were trying to develop an analytic equation to model the molar enthalpy of a binary mixture, right, typically it's going to be my molar enthalpy as a function of composition. Okay. And so this is our expression that we'll have from problem 2, which we'll look at momentarily. And we'll talk, subsequently in lecture about developing said analytic equations for, my binary mixture. But what we're interested in here, or what the challenge is that if I have this expression and I want to compute the partial molar enthalpy of component 1 and component 2, well, the challenge is the definition that I have so far is, let me write down my partial molar enthalpy. The challenge I have so far, or right now, is that if I want to compute the partial molar enthalpy of component 1, h bar 1 is equal to the differential of h total with respect to n1 at constant t, p, and n2. All right, so it's the change in my extensive enthalpy upon adding some differential moles of species 1, keeping everything else held constant. So the challenge with this is, well, how would I evaluate that from an expression like this, right? Knowing that typically we're going to have expressions that are functions of composition. Well, it's going to be multifaceted, right? So first, right, I need to differentiate h total with respect to n1. Right, in my equation here, I have x1, x2, x1, and x2. All right, so what I would have to do is first I'm going to have to go into my equation, right, or go into my expression here, and I would replace, okay, I'm going to replace x1 with its definition. This could be n1 divided by n1 plus n2, and then x2 I replace with n2 divided by n1 plus n2. Okay. And then further, okay, well, I need h total here. Okay, h total is equal to n times h, and so that's going to be equal to n1 plus n2 times h. Okay, so the first thing I would have to do is I would take my original expression, okay, and I would go ahead and I would replace x1 by its definition. So I have this in terms of moles of species 1 and species 2. I do the same thing with x2. And then I also need h total. So I need to take my expression here and multiply it by n1 plus n2. All right, so now I've got this big equation. Well, once I have this big equation that then is only a function of n1 and n2, then I can actually work out my derivative. And then once I have my derivative, it's going to involve n1s and n2. So if I wanted my partial molar property as a function of mole fraction composition, well, then what I would have to do is after I worked out the differential, I'd have to substitute back in. All right, I'd probably have to rearrange and simplify, but then substitute back in my definition of x1 and potentially x2, and then simplify from there. And so it can be done. It's just a little cumbersome. Now, if I have 3 or more components in my system, right, I have to do this. And know that I could always do this. What I want to work out here are some equations specific for a binary system that can simplify this process for us. Okay, so there's our motivation, right? That's what we're trying to get at. Here it's enthalpy. Later on it'll be excess Gibbs free energy, right? We often have equations that are functions of composition, right? When it comes to excess Gibbs free energy, I'm going to have some equation that's a function of composition, and then I'm going to need to know my partial molar excess Gibbs free energy for each component, which is the log activity coefficient. Okay, so this is going to come up, and I'm just looking at more simplified ways to be able to do this. Okay, so what I'm going to do, right, is I'm going to keep working with some molar property f, right? Remember, f is just some arbitrary thermodynamic state function. I use f in a lot of our derivations in chapter 9 only because you can replace f with any whatever thermodynamic state function you're interested in, right? So F could be replaced with V, G, H, U, S, whatever you want. Okay, so we're just keeping it general. All right, so what we're going to do here is we're going to take advantage of our Gibbs-Duhem equation and our expression of how to compute F from my partial molar properties, and we're going to evaluate this for the case of a binary mixture. Okay? And so what I mean by that is first my Gibbs-Duhem equation. Okay, so my Gibbs-Duhem equation is my zero-sum equation. So in general, we had the sum over I, xi, df bar I is equal to 0. So for binary system, that's going to be x1 df bar 1 plus x2 df bar 2 is equal to 0. The other equation I'm going to use is that in general, f is equal to sum over I, xi, f bar I, which for a binary system, I have that f is equal to x1 f bar 1 plus x2 f bar 2. All right, so what I'm going to do is, so here, right, I've got my Gibbs-Duhem equation that involves differentials of my partial molar properties. And so I'm going to take my expression here for f, and I'm going to work out an expression for the differential. Okay, so let me insert another page just so I can keep going. Okay, so I'm going to take my expression here. Okay, I'm going to take this equation, and I'm going to take the differential of it. Right, so I'm going to work out an expression for the differential of f. And so if I do that, I have df is equal to, well, uv prime, right? So x1 df bar 1 plus uv prime f bar 1 dx1 plus uv prime x2 df bar 2 plus vu prime f bar 2 dx2. Okay, squeeze it in there. All right. Well, I have my Gibbs-Duhem equation, so x1 df bar 1 plus x2 df bar 2 are equal to 0. So that's x1 df1 plus x2 df bar 2, right? That's equal to 0. So I'm left with then df is equal to f bar 1 dx1 plus f bar 2 dx2. Okay. So next I've got x1 and x2. Remember, x2 is just equal to 1 minus x1. So therefore, dx2 is equal to the differential of 1 minus x1, which is just equal to the negative, I'm not going to be able to squeeze it in there, is equal to the negative of dx1. Right? So dx2 is equivalent to negative dx1. So this is df is equal to f bar 1 dx1 minus f bar 2 dx1. And that's going to be equal to, factor out dx1 times f bar 1 minus f bar 2. So we have then that df dx1 is equal to f bar 1 minus f bar 2. Okay, so 0.1. All right, and this is actually cool. So the change, right, of f with respect to x1 is equal to the difference in my partial molar values. Okay. All right. Cool. Right. So now what are we going to do with this? Okay. Well, I'm gonna do another. I could do a number of things. Right. Well, one is I'm going to come up to this equation. Okay. And I'm going to get this. So on the right hand side, I have a difference in f bar 1 and f bar 2. And I'm going to replace my equation here, right? And I'm going to see what happens. Okay. So, all right. So I come back up to that expression. And, okay, so returning back, we have f is equal to x1 f bar 1 plus x2 f bar 2. Okay. So now I'm going to do a similar replacement in terms of x2. Right? x2 is equal to 1 minus x1. So I have f is equal to x1 f bar 1 plus 1 minus x1 f bar 2. Okay, so that's going to be equal to x1 f bar 1 minus x1 f bar 2 plus f bar 2. So collecting terms, I'm going to have x1 f bar 1 minus f bar 2 plus f bar 2. Okay, and this is all equal to f. Okay, cool. Okay, well, f bar 1 minus f bar 2, all right, that's equal to df dx1. Okay, so I have f is equal to x1 df dx1 plus f bar 2. So therefore, okay, f bar 2 is equal to f minus x1 df dx1. Okay. So the first relation I have is to calculate the partial molar property, partial molar f of component 2 in my binary mixture is just equal to f, right, the expression I have, minus x1 df dx1, where now my derivative just involves a differential of f, right, with respect to x1, right? So if I have an expression for f as a function of composition, this, right, I can more readily do, handle, perform. Cool, right? So it's that compared to those expressions I had before. Now to get f bar 1, we could do it in a couple different ways, right? Option 1 would be, well, f is equal to x1 f bar 1 plus x2 f bar 2, right? Where now I have an expression for f bar 2. Okay, and actually I could even, simplify it in terms of this equation here, right? I could plug in my expression for f bar 2, okay, here and here, right? And then, so, okay, let me just write it down because, so I'm going to go to this expression, right? And then what I'm going to do is I'm going to collect these terms here, right, which involve f bar 2. So I'm going to have f is equal to x1 f bar 1 plus, and you're going to tell me I'm crazy, right? Because that's just f bar 2, right? 1 minus x1, okay? And that's just x2, right? Okay, professor, you're crazy, okay? So, all right. So let me plug in f bar 2 there, right? And then we'll do option 2 as well, where we could have switched the substitution before. Okay. All right. So f is going to be equal to x1 f bar 1, okay, plus x2 f bar 2, and that's going to be equal to f minus x1 df dx1. Okay. So f is going to be equal to x1 f bar 1 plus 1 minus x1. Okay, and this is if I want to get everything in terms of x1. I could also get everything in terms of x2. Doesn't matter. F minus x1 df dx1. Okay, so if I expand, I have f is equal to x1 f bar 1 plus f minus x1 df dx1, put plus, and then minus x1 f plus x1 squared df over dx1. Okay, and so now we're just going to simplify. Okay, so f is equal to, so I'm going to collect terms here, right? So what I mean by that is I'm going to factor out an x1 df dx1 right here. So if I factor out x1 df dx1, okay, then it's going to be one of these terms, so it'll be an x1 minus 1. So that takes care of these two terms. And then I'm going to do the same thing with f plus, okay, I'm going to have f, and it's going to be a 1 minus x1. Okay. So that takes care of these two terms. And then plus x1 f bar 1. Okay, cool. So, let's do it. So I'm going to do a couple more things. So then f is equal to, so x1 minus 1, right? So that's really negative x2. So I'm going to write this then as a negative x2 x1 df dx1 plus, so now 1 minus x1, so that's plus x2f, just to simplify it, plus x1 f bar 1. Alright, so now I'm going to bring these terms over to the right, and so I'm going to have f minus x2 x1 df dx1 plus x2 minus x2f. Oh, I gotta get my terms right. So f plus x2 x1 minus x2f is equal to x1 f bar 1. So if I start by, I'm going to simplify the right hand side a little bit. So I'm going to group f. So this is f times 1 minus x2 plus x2 x1 df dx1, right, is equal to x1 f bar 1. So if I divide through by x1, knowing that 1 minus x2 is x1, I have the f plus, kill that x1, x2 df dx1 is equal to f bar 1. Oh, so I get to my final expression that f bar 1 is equal to f plus x2 df dx1, okay, and that'd be equivalent to, if I want to keep everything in terms of x1, 1 minus x1 df dx1. Right, now I'll make the note that my derivatives now just involve x1. Right, so it'd still be the case, I could do a couple different things, but it'd still be the case that if I were to go up to my original equation that I started with here, all right, this is in terms of x1, x2, all right, I would still need to replace x2 with 1 minus x1, right? So I would need to replace x2 with 1 minus x1. And then once I did that, right, now though I just have a differential of f with respect to x1. So here's my equation for f bar 2. Here's my equation for f bar 1, right? And so this is one way of getting at it once I have f bar 2. All right, I also just could have gone up to where I'd made the substitution before and solved or put things in terms of x2 instead of x1 and gone to the same place. Okay, so the motivation for this, okay, or bringing it back to where we started, is if I want to, so if I have expressions for my molar properties in terms of mole frac, if I wanted expressions for my partial molar properties, I would need to replace mole fractions with their definitions in terms of moles. I would need to take my expression and multiply it by n so I get my extensive value. Then it would have to differentiate. If I wanted things in terms of moles, I'd have to divide through by n to make it molar. I'd have to try and substitute in mole fracs in terms of my moles. So there'd be a lot more algebra that would need to be performed. Okay. And so with these expressions, right, with these simplified expressions for a binary system, right, now on the right hand side it only involves a derivative with respect to mole frac. Right, so I would still need to replace x2 with 1 minus x1 in that expression that we started with, but now I just have an expression that only involves derivatives with respect to composition. Right, so only involves derivatives with respect to composition, which would hopefully make things simpler in terms of calculating and evaluating. Right, so hope that helps. This is also typed up in our typed up notes, and then we'll use this in problem 2 next. Okay, see you in class.